lambda homology. Okay, that's bad. Homology and cohomology. And what Poincar introduced is more interesting invariance called fundamental group. And also, for Riemann manifold, you have to introduce metric, curvature, connection, and so on. So these are very, very basic tool to understand the manifold in high dimensional manifold. It turns out that it's very important to understand even physics. So for instance, Riemann geometry. So Riemann geometry. So this is called Riemann geometry. Geometry is related to so-called the general relativity. So GR is constructed based on Riemann manifold, and also homology fundamental group. This is very close connection to the so-called. There are lots of applications, too many applications to physics. For instance, one is called. People just consider topological phases. Phases in condensed matter physics, and also let's see what it's called. Let's see. Oh my goodness. Topological phases, many things. I mean anomaly, and also let's see. What I try to say, Chern class is used for, anyway, many things, topological phases, anomaly, and so on. And also, one has to learn so-called Lie algebra and Lie group. So this is used for standard model. Model of particle physics. It's important to learn physics. And also what we are going to learn is called vector bundle. So that generates the notion of tangent and cotangent bundle, vector bundle, and then G bundle, principal G bundle. So this is important to describe so-called Yang-Mills theory. Yeah. Topological phases, and also another topological invariant. So the Euler calculus is one topological invariant. There are lots of topological invariants. More sophisticated topological one can introduce. So topological invariant, as a matter harder of it. So for instance, Chern class. I mean, anyway. In English it's called Chern class, but I mean Chinese is Chen, right? Chen. Anyway, but I call it Chern. But the old characteristic classes so these are very essential to describe anomaly. anomaly is the phenomena, the symmetry is broken at the quantum level. So in quantum field theory, you have to deal with infinite dimensional degrees of freedom, which is usually hard. But one can associate some quantity in quantum field theory to the topological invariance, so whatever. So certain quantity, so-called anomaly and so on, anomaly to the topological quantity invariant, and that is so-called invariant under so-called renormalization group rule and so on. There's a very powerful tool to analyze what's going on in quantum field theory. That's called anomaly, and this anomaly plays a very important role both in quantum field theory or particle physics and also condensed matter physics. Nowadays, people just study topological phasing and so on in condensed matter physics. The understanding this topological invariance is very important. So I hope you understand this language, which is developed by mathematicians, are very important to understand indispensable to understand the physics, the nature of the physics of nature. When did we start? 9:55. Okay, let's see. Okay, so then I will give you one example how the okay, so I will take one break in the middle, like 10 or 15 minutes. That's it. So I will move continue a little bit. So I will give you the one example that is one example in physics that treats Euler characteristic in intrinsic way. So hopefully, so I introduce the so-called Euler characteristic, and then that is the that was introduced by long time ago by Euler. I'm not sure. It's maybe 18th century. I don't remember. But 1982. So one genius introduced the Euler characteristic in physics in very intrinsic way. So this is called one genius is called Witten. Introduced so-called the time model of the quantum field theory. What's called nowadays called topological quantum field theory. Acronym in TPFT. So let's consider the following way. So let's consider the partition function. So this is just an integral. So this is just integral, but so it's called Gaussian integral. But this is a toy model, so-called passing. So this is called toy model. So toy model passing. Passing, you need to deal with infinite dimensional degree of freedom, but now it's a finite dimensional analog. And as a matter, so you already know that the Gaussian integral. This is a Gaussian integral. So people have to be familiar with. So Gaussian integral. So therefore, when s, the function s, takes the form of, for instance, like this way, if s of x, the function of s of x takes the from minus infinity to infinity, like this way. Minus infinity to infinity, one can apply this Gaussian integral to this partition function. Then z equals to 1. On the other hand, if the s of x, okay, so s of x takes the infinity to infinity, or minus infinity to minus infinity. For instance, this is minus infinity to, at the end of that, minus infinity, right? So therefore, the integral doesn't matter. So at the end of the day, so dx dx times ds over dx will give you ds. So that boils down to this one. So at the end of the day, minus infinity to minus infinity, you get 0. Okay. So therefore, this one you get the z equal to 0. Okay. So therefore, if the s of x, if you consider polynomial a of x to n plus lower degree polynomial, when n is equal to z is, if s of x takes the polynomial form whose highest degree is n, okay, then z is equal to 1 or 0 depending on n is equal to odd or even. So if it is an even function, so it becomes minus infinity to infinity or infinity to infinity. Okay, so it's the partition function is 0. If it is odd function, it's minus infinity to infinity, so you get 1. Okay, depending on only depends on the n, the case that the n is even or not. You can determine the partition function z or integral z without knowing the explicit form of the potential. Okay? This is only sounds like what we have learned in the order characteristic. Whatever metric we introduce, at the end of the day, if you integrate out, you get the order characteristic. Okay? So here, the integral doesn't matter, the form, explicit form of s. Okay? It only depends on the degree, highest degree of polynomial, the polynomial function. So to see it more explicitly, one can introduce so-called oscillator integral or whatever. Localization, it's a technique of localization. So one can scale s goes to t times s of x. Since t is some real number, t is a real number. So since the integral itself independent of the explicit form of s, we can just scale the potential. So that so if you take t goes to infinity limit, okay, t goes to infinity limit, so this quantity becomes very big. Since there's a minus sign, it goes to 0. Exponential of minus infinity is 0, right? So therefore, so only contribution you get is s of x is 0. Before t goes to infinity, if s of x is 0, exponential minus z times 0 is just 1. Okay. So, but however, there is a so-called quantity or called ds over dx. Therefore, once you take t goes to infinity limit, everything localized into the s of x is 0. For instance, everything localized, the point s of x is 0. This point, this point, this point, this point, this point, this point, this point. So this is sum over sine. So this becomes when s of x is 0. So what matter is only this ds over dx, the sine of ds over dx. Okay. Once you take t goes to infinity, and this already look like so therefore this is sum of s of xi is equal to 0 plus minus 1. So for instance, for this cases, so ds of the plus 1 and minus 1 plus 1. Okay. So it's just slope. Slope is negative or positive. Okay. And here plus 1, minus 1, plus 1, and minus 1. If you sum them over, you get 0. Here you get sum them over, you get 1. Okay. It only depends on when n is even or odd. That's how we look at the when once you take t goes to infinity. And then do you remember this form of this summation? It looks like something, right? Already. Well, it looks like what? Yeah. So it's a Poincare-Hopf theorem. So sum over all the index of the 0 of the vector field will give our characteristic. It already looked like Poincare-Hopf theorem. So this is a basic notion of the basic way to look at okay, so one step toward so-called topological quantum field theory, TQFT. So by looking at this, so Z, to look at Z in partition function, more physics way, one has to introduce so-called Riemann variable, and then introduce the form so-called. So this is dx, this is d chi, and d rho. Exponential. Okay, chi is a bit confusing. Let's use some other variable psi. So psi and rho are so-called Grassmann variable. So that the chi, no chi, sorry, psi. So psi rho, if you swap them together, you get sign, negative sign. That's Grassmann variable. And also integral over d psi d rho, d psi d rho, d psi d rho psi is equal to 0. Only d psi d rho psi rho, or it depends on the order, rho psi is equal to 1. So this is so the role of Grassmann variable. So once we integrate over rho and the psi like this way, so you can just do the Taylor expansion of the exponential of this term. And then what you get is integral of rho of psi here, and then what you obtain is this term. Okay. Once you integrate psi and rho, you get this measure. So what you just mimic, a bit modify this simple Gaussian integral by introducing so-called Riemann variable. Then it looks a bit more in physics, which is the it's a bit more look like a physics, and we call this quantity as Lagrangian. And this will look like more like a path integral. So cool. And this Lagrangian has a remarkable symmetry. So this Lagrangian has symmetry so that one can check that the delta x is equal to psi, delta rho is equal to s of x, delta psi is equal to 0. Okay, as you can, it's a good check. So delta L. So under this transformation, so let's look at the transformation. This becomes minus s of x delta s of x plus delta rho ds dx d psi psi plus rho ds dx delta ds dx. Since and then psi, psi. And since delta psi is equal to 0, you don't need to take into account delta psi. Okay. Let's see. So then you just apply this transformation rule. So this is minus s of x, s prime of x, psi. Okay. Prime is just derivative. And the plus delta rho is s of x. And s prime psi. Okay. And then since the dx is some function of x, okay? Some function of x. But the transformation of x will give you psi, okay? If you have a 2 psi, it's a Riemann variable. Psi is equal to minus psi. If you swap them together, you get the minus sign, okay? So therefore, psi should be 0. It should be 0, okay? So once you apply delta on ds over dx, you get some psi, but psi cancel with another psi. So this will go away, okay? So therefore, you just look at this one and this one. It's just the same quantity with different sign. Therefore, this is 0, okay? So this Lagrangian is invariant under this transformation. So this is called symmetry, okay? And the people call it BRC symmetry. So the reason why it's called BRC symmetry is that the so for instance, if you do that d square x is d psi is equal to 0, so delta square is equal to 0. Okay? Delta square is always 0. So that's called BRC symmetry. So one can check delta square x is delta psi equals 0. The same thing happens delta rho. Delta square rho is delta s of x. This is s prime of x chi. Okay. So and then this becomes 0. sorry, this is psi, sorry, this is psi equals 0 because of the equation motion. So equation motion with respect to, if you take Lagrangian, so this is the S of x prime psi, okay? So this is the equation. If you impose the equation motion, this comes to 0. Okay? So this Lagrangian has a BRC symmetry, which is the outer square equals 0. This is also analogous to so-called the most basic relation in the drum cohomology. It's called D is called differential in drum cohomology, and if you take dd square, you get 0. So it's related to the so-called cohomology. I already erased the notion of cohomology. So this is related to so-called cohomology, which is some version of which is related to cell decomposition I talked at the beginning. Okay. So yeah. Okay. And also this. So what we have looked at is this. Everything locals S of x equals 0. Okay. S of x equals 0. This integral is localized S of x is 0, but this S of x 0 is this one equal to 0. So the usual property of TQFT, topological quantum field theory, once you take the BRC transformation of the Fermat field, so Grassmann field. So this Grassmann field is Grassmann variable is introduced to describe a Fermat field. So if you swap the Fermat, you get the minus sign. So once you look at the BRC transform Fermat, everything localized to the BRC transformation of Fermat to 0. So this is the basic property of topological quantum field theory. So everything localized to BRC transformation of Fermat field. So that's the so that's the typical feature of the quantum field theory, and then so this is a pi model of the topological quantum field theory. So this looks like the finite dimensional analog of the Feynman path integral, where Lagrangian has BRC symmetry. And one can mimic the consideration to higher dimensional. We just introduce the following thing. So D is equal to sum over n. So you just introduce a lot of variables. That's dxi square root 2 pi exponential minus 1/2. Okay, so I think I just write down the following d rho I, d psi I, and e to the L, where L is equal to minus 1/2 sum of here everything sum of I and j. So you just introduce lots of variables, and at the end of the day, what's going to happen? Everything localized, this derivative is equal to 0. So instead of s of x, now I just introduce derivative with respect derivative of w with respect to x. So therefore, this one indeed localizes the sum of all the W is derivative equals 0, which is called critical point. And then a sign of determinant. So this part is now become, after integration long psi, this will give you so-called determinant of the metric. So I and j runs from 1 to n, so it becomes a matrix. Okay. So you have to, after integration, this becomes determinant of matrix. The determinant of this called partial I, partial j, and w. So in physics language, this W is called potential. Some people call superpotential. And mathematical language, this is called Morse function. Okay, Morse function. Mathematical language is called Morse function. And then this derivative equals W equals 0 is called critical point. And this quantity is called Hessian. And what we have solved is that for instance, what we have solved is that we introduce height function. We'll introduce height function. For instance, we introduce the height function, okay? And then look at the vector field, gradient vector field, with respect to this height function, okay? And 0 is south pole and north pole. In the case of sphere, you have, in the case of torus, you have top and bottom. In addition, top and bottom, you have two saddle points, okay? Two saddle points. This point indeed corresponds to once you take W as a height function, okay? W is a height function. This critical point really corresponds to 0 of the vector field. This is a critical point, as you can see. As you can see, once you try to change W here, you cannot. So once you try to change around here, W here, so derivatives with respect to the local coordinate 0, right? So you cannot go. You cannot change W infinitesimally around this point. Okay. However you move, infinitesimally derivative, first derivative is 0. And this Hessian, determinant Hessian, sign of determinant Hessian really corresponds to the index of the vector field. Therefore, this quantity Z is really give you the order characteristic of manifold M. You consider this path integral. This path integral can be considered any manifold. And this finite dimensional path integral will give you order characteristic independent of the choice of potential, W, Morse function. Morse function can be chosen arbitrarily. Okay? In such a arbitrary, generically arbitrary. Okay? So there is some weird potential that doesn't satisfy some condition. The critical point has been non-degenerate and so on. But anyway, so generically one can choose superpotential arbitrary way. But at the end of the day, path integral only depends on the topology of the manifold. Okay. So this is the time model of the quantum field theory. And at the end of the day, without performing integral, one can obtain the body of partition function. Without performing, okay. So that's the powerful of topology. That's a power of understanding topology of manifold, or what's the how to say benefit of understanding mathematics, or differential geometry and topology in physics. So let's take a break. 10 minutes break. Yeah. Oh, by the way, can you create a widget group now? So S some polynomial. We assume some polynomial. Whatever. And once you take D, so S prime of X is n a x n minus 1 plus lot of dot. And once you apply delta X, so n minus 2 plus dot dot dot. I think we times n minus 1. So once you apply delta X on here, you get the psi, right? You get the psi. So delta X to the n minus 1 is equal to n minus 1 x to the n minus 2 psi. And since we have rho delta S prime psi, substitute this rho n minus 1 x n minus 2 psi psi. And the psi will give me. Do you understand? Do you understand psi equals 0? Yeah. That was just function. With you need to start with the property, but generically it's a function of x. No, I just realized it's a function.
more and more places approach the sphere. So we can see the sphere I think this is weird because you don't have any, you have one face, you don't have any edge and don't have vertex. So can we directly cut this one?
I mean, one can just even if okay, then one can do is just following. So you have a two problem.
Jesus.
So you have a two disk. You have a two disk. And if you identify this boundary, you get see. So you have a two face, one edge.
Does it have a vertex?
To have an edge, you have to start motor.
Oh.
So you have to identify this point, one. You don't need to. So did you create a widget group? So he has created a widget group, so you can just join this widget group. Can QR code?
You can join a private group and the code is 5678.
So just tell all the students how to join the WeChat group. I don't know how to do that.
How we start?
Huh?
How we start?
No, no, yeah.
I have a question for what does this mean? Delta L divided by delta rho equals S prime x.
No, L is just correct. If you take a derivative rho, so you get this.
Because I will have delta L, you can transfer.
No, this delta is BRC symmetry. I just take a derivative with respect to rho.
This is different.
Different.
So I have a doubt that why this is canceling 0. Because you use delta square.
No. So here, delta of the BRC symmetry x will give psi. Psi times psi is
The product of psi is 0.
psi squared is 0.
But this is S prime. Yeah, but you have delta S prime x, y, you get delta x.
Just think about it. S prime is some function of x. If you apply delta of x to the n, you get the psi.
Oh, we just take S like
Some function of x. Psi? Yeah. Yeah. So just send me a message via WeChat. What students' numbers on. So did you tell all students? Okay. How to join the WeChat group? Oh yeah. So just send your. So if you want me to put you into e-learning, just send me your name and then student's number. I think that's enough. Oh yeah. So shall we start? Can I get one drink from downstairs? Or is there any way to get the water? Downstairs. Okay, I'll get the water from downstairs.
That way, opposite way, sir.
Okay, let's get started. So I think you need to spend. Oh, by the way, yeah, I need to mention one thing. So on Saturday there's a class, and what time I ordered for 1:30? 6, 7, 8. So it starts from 1:30 or something. So day after tomorrow we will meet again here. Okay. And then I will post the homework to this evening. I'm not sure. Okay. Anyway, let's not talk about it. I think you need to spend some time to every week to solve the homework. But to really learn something, I think you need to make hand dirty, and then try to solve homework or so on. It's not easy job, but it's better to do that to understand the subject. I'm also going to teach the string theory course this semester. I don't know how many of you guys will take both, but even string theory, I will give you homework. So if you're brilliant enough and also spend significant time on solving homework, you can take two courses, my two courses. But otherwise, if you want to spend some time on research or something, some other courses or some other life and so on, it's better to take one course, register one courses, and take one course as an auditor. Otherwise, I mean, you need to spend significant time every week on the homework. But anyway, that's your choice. I mean, if you think you can do it's doable, you can do that. But I just mentioned that the string theory I only teach every 4 years. I will teach string theory every 4 years. So anyway, if you stay at Fudan more than 4 years, you can take another chance. Anyway. So anyway, so let's get started. So this is the prologue, and so last 50 minutes or so, I will go into the beginning of lecture. The start about talking about But anyway, so the physicists, historically, there's a time that physicists do not know about this kind of like a differential geometry and topology so much beyond the GR. That kind of situation, this poor situation has been changed drastically recently due to huge development of the even like topological quantum field theory, supersymmetry, topological phases of matter, condensed matter physics, anomaly, and so on. So this language is very, very important for physicists, even physicists. And even mathematician starts learning something out of from physics prediction. So it's very important to learn, even though at the first glance it's a very look like mathematics or whatever. That's not how the modern physicists think about this differential geometry and so on. So it's not only the general relativity, but also many fields in physics nowadays use the differential geometry and topology as a tool to study physics. Now, on the other hand, a mathematician also, the geometry learns many things from physics, from over quantum physics. So it's very important to learn this subject. So let's start our journey to learn a difficult subject. So let's first introduce the manifold. So yeah. So I drew the two-dimensional surface just before, but to introduce the notion of high-dimensional manifold, one has to decompose into patches. So the notion of the manifold is just that as follows. So the M is called n-dimensional manifold. If one is n is union of some union of open covering U alpha. So union of open covering and then two to the continuous function such that the continuous important smooth. People call smooth or differential. Manifold continuous and invertible map phi alpha U alpha equals to phi alpha. This is also open. And 2, 3. I'm going to explain everything. Don't worry about it. It's going to be difficult, but don't worry. So any alpha and beta. So let's. So there is a manifold m-dimensional manifold, and the open patches is that you have open. So this is U alpha, U alpha, and another open patches. U beta. So then there's a map by alpha, which is inside Rn. You know Rn, right? Rn can be understood as some coordinate which is found by n variable. Okay? We are staying in three-dimensional space, but we can easily generate increased number of coordinates, even though we cannot imagine. And you can just consider the open. So phi of alpha is something like inside. So this is phi phi alpha u alpha. And then there's an overlap region here, is here, and here. Okay. So inside Rn, there's an open region. Open is the, I'm not gonna, oh yeah, so I have to say, so in section 2 is the collection of my lecture notes, the collection of the definition, basic definition. You can use it as a dictionary. So I'm not gonna explain everything about the definition and so on. It's going to be a bit boring, and also it's very mathematical. I'm going to skip. So one can introduce so-called notion of topology in Rn. So one can define so-called open and closed. Open is the, for instance, you cannot have a boundary. You cannot have a boundary. And then, so Rn itself is open, and then one can have, if you have a boundary, if you include boundary, it becomes closed. Okay? But you can define very, very rigorous way, but which I'm going to omit. But anyway, so you can just look at some region which is open inside of Rn. Okay? So this part is mapped to open region inside of Rn, and it's a one-to-one. Okay, for instance, you cannot have this point and this point. Okay? So there is 2 point goes to 1 point. If 2 point goes to 1 point, it's not invertible. Okay, so this point cannot go to 2 point, right? 2 point. That's not invertible. So it's a one-to-one map. And if you introduce so topology and so on, so one can define the meaning of continuous. The continuous. But I'm going to omit. So it's a, I mean, intuitively obvious for physicists, but for mathematician, you have to introduce rigor. So, but which I'm going to omit. But I mean, intuitively, you can just differentiate how to say, the 2 point cross together goes to just 2 point cross together and so on. And you can just differentiate, and you can have a meaning of differentiation. So then, so you get another map phi beta, which again map phi beta u beta open region, another patch of another Rn, another inside Rn, and there's the overlap region here. Okay, so that's the third. So for third, what you have is the phi beta inverse phi alpha. Is smooth. Smooth. Sorry, so from here to here you cannot define a differentiation, but I'm sorry, I told you wrong. From here to here you can define something notion to call continuous. But the so smooth or differential means that the so beta inverse alpha means that so this overlap region has a meaning beta inverse and go to overlap region and alpha beta inverse, phi alpha inverse and go to this overlap region and send this part into the here by phi alpha. That's what it means, phi beta inverse phi alpha. So this point goes to overlap and go to here. Okay. So then phi beta u alpha intersect to u beta is this region. Okay, is mapped phi alpha inverse and go to here, this point. But now, so this is a map from Rn, the pointing Rn to pointing Rn. Okay. So this is the point inside Rn. So this is Rn, and this is another Rn. So now there is a map from Rn to Rn. So one can introduce the notion of continuous. You can differentiate with respect to these coordinates. Okay? So therefore you can, if it is differentiable, it's called smooth manifold. So if you learn the GR, physicists often write down the manifold local coordinate dx mu dx1 to or whatever x1 to, people write x mu is equal to x1 to xn and so on. This is really the map. So in GR, people just write down the local coordinate as x mu, and this x mu is really the meaning of this map phi alpha. It just gives a meaning inside of Rn, okay? The coordinate. So therefore, U alpha and the phi alpha gives local chart, local coordinate chart. And then collection, U alpha and the phi alpha, collection of alpha is called atlas. And then this phi alpha is the x1 dot xn is called local coordinate. Okay, let's follow the physicist way. Local coordinate. So this is local coordinate means really the coordinate in Rn. The physicists usually use. So important point is that what is the smoothness? For instance, so it's hard to analyze the manifold without doing anything. Usually, what people would do is just send a manifold M to some space, other spaces. For instance, R. So as I mentioned, so if you have the height function is just that this point is mapped to Rn. R in this point. This is height function. This point in M, point in manifold M is mapped to point in R. So this is called height function. Okay. And if you have this local coordinate, like a chart, so one can define the phi alpha of U alpha is mapped phi alpha inverse to F is to R. So therefore, the point, if you have this chart, you can use by using R. So the point in Rn, and just go back to this manifold point in a manifold. Then after that, you can go to the R. Okay. At the end of the day, it's a map from some point in Rn to R. Okay. So therefore, one can define the notion of smoothness. Okay. One can differentiate. So therefore, to introduce the local chart is you can do then locally the differentiation and so on. So example. So why do we need this local coordinate? Is that we have a topology. Not everything is like a Rn. As we saw in the first lecture. No, not first lecture. The first part of the lecture. So natural thing is so example is an dimensional sphere and a sphere. People write down Sn, which is x1 dot xn plus 1, or maybe I should write down 0. Yeah, sorry. My definition is u0 dot un inside of Rn plus 1, and that satisfies sum of u squared is equal to 1. So the length is one. This is just usual notion that the S2 is U0 square plus U1 square plus U2 square is equal to 1. So it's inside R3 S2. So you can draw like this way for 2 sphere, but you can generalize for n sphere, the high dimensional analog. You just it's the length, the position whose length is equal to 1. Okay. So then, how do you define this local coordinate? The question is local coordinate. So that's what Riemann has done. So take. So for now, I consider this one as the inside Rn plus 1. Rn plus 1, and look at the intersection. So this is great. So this now in the equator is like in the equator is what? What? Just speak out. Yes. N-1 dimensional sphere, okay? And N-1 sphere. So look at the south pole and north pole. South pole, north pole is defined. Okay, so there's a typo in my lecture note. So you just look at the south pole is U0 is equal to -1, and then north pole and the U0 is equal to +1, and the other entry is 0. Okay, the other entry is 0. That's the south pole, north pole, and look at the open chart is open U plus as a sphere and get rid of south pole. And U minus is get rid of, am I doing, okay, north pole. So it's an open thing. So then one can define phi plus is a map U plus goes to Rn. U0, U1, Un is mapped to 1/1 plus U0, U1 plus. So what this function does is as follows. So let's look at the U plus. U plus is the sphere, and just get rid of this point, south point. You just get rid of this point. So what we are looking at the U plus is just get rid of this point. Look at the other all n-dimensional sphere except this point. Okay. Then what this map does is as follows. You just write down. So you just pick this south pole. Pick this south pole and pick some point of the sphere. Let's pick this point and just draw the line and connect. So this point is defined U0 UN. Some point which satisfy length is equal to 1. Okay. And just connect the south pole and this point, and it hits just extend this line until it hits this plane, this Rn plane. This is Rn inside Rn plus 1. So this Rn cuts through this equator. cuts through this equator as a n-1 dimensional sphere. Okay? And it hits some point, this one. Okay. So the map is that this point on the sphere is mapped to this point on Rn. Okay? That's this map has done. So the reason why we need to get rid of South Pole is that you cannot draw the line from South Pole to South Pole. It's just many tangential lines, so you cannot uniquely define the map. Another way to see that if you put u0 equal to -1 into here, it diverges. Okay, 1/0. So you cannot define this map if you include this South Pole. So you have to get rid of it. So that's the open U plus that corresponds to this red part. Okay. Another map is phi minus U minus or R to the N. It's the same similar map, but now you just connect North Pole to this point. Okay. So this point, and it's just connect North Pole, and in between it hits this plane, Rn plane, somewhere around here. Okay. So therefore, this is phi minus of P, and then this is phi plus of P. Phi plus of P, and P is this point. So the P is this point. Okay. So under this what I call coordinate chart, the point on the sphere, the same point on sphere is mapped to different point on Rn. Okay. And then, as I mentioned, so this U beta is the, I think I use different color in that case. Okay, maybe you can think of the U beta, this U beta is U plus, and the red one is U minus, whichever. U minus, you just get rid of this North Pole and look at the other part, okay? Okay. So then, what is the intersection here in sphere case? What is the intersection between two charts? Huh? Yeah. So the intersection is the sphere minus North and South Pole. North and South Pole. So okay. So we need to understand the map from here and go back and then this point. Okay, so that's what we need to understand. So to understand this map, we need to understand that the inverse map, phi beta inverse. So now we need to understand the inverse of this map. Okay. By the way, so this local coordinate is called graphic stereographic projection. So now let's look at the inverse of this one. So f plus. I mean, just a straightforward exercise of geometry you have learned and whatever. So just map this point, okay? Again, just connect the given point, a point on the Rn, and just connect to the south, either south or north pole, and just look at the point that hits on the sphere. That's the inverse map, okay? So plus minus is Rn goes to U plus minus, that is x1, xn. So x1 to the xn, so is the coordinate of this one. Okay, whereas this one is the coordinate u0, the total un. So to pick a point on Rn, you just connect. So this is connect this point with north pole and keep some point on the sphere and just map this point to this point. This is the phi minus inverse. Yeah, phi minus inverse. Okay, do the same exercise. So just connect this point with south pole, and you hit some point here, right? That is this point is mapped to this point. That is phi plus inverse. Okay, phi plus inverse. Okay. And then you can do the just usual Euclidean geometry analysis, so that the one can convince himself 1 over 1 plus x squared, then plus minus 1 minus x squared, x1 dot 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 xn. So this is a map. What does it mean? So for instance, if you look at the what does it mean? If you look at the point on the great circle, this great circle, okay, it's not great circle, so equator, which is n-1 dimensional sphere, is the intersection between this Rn and this sphere, right? So therefore, the map, inverse map, is just connect this equator and this, for instance, north pole, and it hits the original point, right? So therefore, as you can see, when the absolute value of x is equal to 1, am I doing crossing? Hopefully I'm doing correct thing. So when the yeah, I think it's just 2 times this one. Sorry. Yeah, sorry. I think it is 2 times. I think it's typo. So when absolute value of x is equal to just 1, it's just a point on this equator, right? Absolute value equal to 1. So then this map, it just goes to the original point. So therefore, it should be, so this absolute value is equal to 1. It's on the great circle, it should be 2, sorry. So it's normalized, when you substitute absolute value of x equal to 1, it's 2 over 2. And you just substitute 1 minus 1, it's a 0, and the original coordinate. So it's just identity map. If on this equator, okay, on this equator. But if you change the point from the equator, for instance, if you take the origin, okay, of the Rn, Okay, it goes to South Pole, right? South Pole. So therefore, if all the point is a 0, all the point 0, absolute 0, and then 0, 0, 0. So then what's going to happen is why the normalization is not correct. It goes to -1, 0, 0, 0, but normalization is not, looks like incorrect. Well, what is the correct normalization? I got confused. Maybe 1 is okay. I think I made some mistake on the normalization. Sorry. Yeah, I think some normalization mistake has occurred. Why is it not correct? Sorry, I will take a look at, I think I made some mistake on the normalization. I think some normalization is not correct. Why is that? Oh, now I understand. I think I should put 2 here. Square 2, square 2. So what I have to do is you have to do square it. So 1 over 1 plus x squared, and then 1 minus x squared plus sorry, I think I made some stupid mistake on the normalization. I cannot fix now, so I think I would correct next lecture or so. I think, why did I make a mistake? So I think it should be, in that case, 2. So if it is 2, everything should be okay in that case. Yeah, I think this is correct normalization, I think. Sorry, I made a mistake. Hopefully this is okay. I think I need to think about it. Yeah, I think this is okay. Now I understand. This is okay. Sorry, this is typo. So this is 2 times x1, 2 times xn. The one way to see is as follows. So if you do square it, you have to be plus 1. 1 plus x squared, and then 1 minus x squared plus 2 times 2x squared, right? So if you square all the coordinates, you just take the absolute value square, then what you get is 1 plus 2x squared plus x squared x to the 4th. And if you look at this one, it's times 1 minus 2x squared plus x to the 4th plus 4 times x squared. Okay, and if you add them up, it becomes let's see. So if you add them up, you just erase this one and it becomes plus sign, and they cancel. It becomes 1. Okay, so that's a 2 times this one. So this is typo. Sorry. So if you find a typo in the lecture note, just let me know. Okay. So this is the correct normalization. Sorry. So as you can see, So if you pick some great equator, so it's just absolute value is 1. So therefore, if you substitute 1/2, and here you just get the 0, and the 2x1 dot 2xn, and 2 cancel, it becomes original point. It's just identity map. Whereas if you pick some origin, all point at 0, it goes to South Pole. And as you can see, if you put the 0 here, it's just 1, and everything 0 except the first entry. And the u0 becomes plus minus 1. In this case, you just pick phi inverse, so that you have to pick minus 1. That's what it means. Okay. So there's a typo in the lecture note. Good. So, and then now one can define transition. So this is called transition function. Sometimes called transition function. Okay, transition function. So phi minus inverse dot phi plus of x. You just compose this times this one of them. Then what you end up is, this is good exercise to do, hopefully with no no typo. Yeah, this is the map. One can define. So what it does is that so start with this point, okay? Start with this point and map to here and map to here, okay? That's a map for phi minus inverse times phi plus. So this point is mapped to here by phi minus inverse, and mapped to here by phi plus. Okay, so that is the you just scale by some normalization, and then I think I just made a mistake here. Hopefully I didn't make any mistake. I'm just worried about, since I made a mistake here, there is some normalization may occur. To be honest, I don't know. But I'll correct it next lecture if I'm wrong. So this is the example of n-sphere, and then so it's compact manifold. It's compact manifold. If you can find finitely many coordinate charts. So if it is the finite, you can find finite many charts. So in this case, only 2 charts needed. Okay, you need a U plus and U minus to cover all sphere and sphere. So it's called compact manifold. Any question? Okay, so now one can introduce the notion of the manifold with the submanifold. So how would you define some manifold? So one can introduce some manifold in the following way. So manifold, you introduce manifold M. I don't think this color will be distinguishable. Let's use blue. So there's a manifold. For instance, let's take a look at that. Oops. Some manifold like this way. And one can take the local coordinate so that this blue line is mapped to like this way. And also local coordinate is such that the phi beta mapped like this way. Okay. Under phi. So this blue one is characterized as the some xn plus 1 So for instance, if you take a look at the x, this coordinate x, is it visible? This blue one, is it hard? Oh, seems like it's hard. So let's write down. So for instance, one can take x and phi plus 1 as follows. And this blue line is characterized by xn plus 1 is 0. Okay? At 0. So some manifold is that so this blue line is in this case, blue line is called n prime dimensional submanifold. So this blue one is called m prime. We call m prime. And m prime inside of M is n prime dimensional submanifold. If all the other coordinate, there's a map from this open chart to here, all the other coordinates are 0. You can take. It's the same thing also here. One can find a map. So for instance, you can see as you already know. So example is here. So this equator is, you cannot see the blue. This equator is S minus 1 dimensional submanifold inside an n sphere, n minus 1 sphere. As you can easily see that so for this point, the coordinate so let's see. So at this point, what's going to happen is that all the other, let's see. So for instance, one can take, what should I? So this direction, you can take this direction. As some other coordinate. So in this case, what should be the answer? So I'm just wondering what I should do is that okay, I see. Maybe I think it's better to use different grace hemisphere. Sorry. I think instead of using this one, so to use to see this to this one, I think it's better to use other grace circle. Let's use this grace circle. Yeah, sorry. So Sn to be this grace circle. So this is also so this blue one is also n-1 sphere inside Sn, right? Okay, and this one is characterized by, for instance, this is U0, this axis U0, and for instance, one can take this axis U1, okay? And the U1 equals 0 is characterized by this surface, this n-1 sphere. So therefore, under this local coordinate, so you just put the U1 equal to 0, okay? U1 equal to 0. Or maybe in this definition, I think it's better to take UN, sorry. UN, so that the, so UN equal to 0, sorry. I think UN equal to 0 is better. So this great circle, n-1 sphere, is characterized by just you put all the UN coordinates to 0. Then in that case, under this map, all the map UN is 0. Okay, the last entry is 0. That is what it means. This x to n q is equal to 0. Okay, do you understand? Do you understand what you mean? So in other words, so under stereographic projection, you just connect this south pole to this this blue line, right? So therefore, everything is under this map. Everything is just mapped to this plane, okay? n-1 plane. Do you understand what I mean? So if you just connect this blue line and put lead, so therefore, inside of this Rn plane, there's a Rn-1 locus that is defined by Un to equal to 0. The other coordinates are non-trivial. Okay, so you just define this. That one is Rn-1, and this blue circle under stereographic projection, it hits only on this red Rn-1 dimensional space. Do you see that? Okay, so that's how you see this manifold inside a manifold. Any question? Okay. Okay. Done. So see you on Saturday, day after tomorrow, and I will put the homework tonight or like within a few hours. And then you can start solving. I think it's better to spend the weekend to solve, even though solving the weekend, and you will see how long it will take usually to solve all the homework. So if you have a question, you can first ask me via WeChat or